We're going to explore Unit 7, Electrodynamics and Relativity, specifically the special theory of relativity. To understand why special relativity was necessary, we need to look at the state of physics in the late 19th century. Newtonian mechanics described the motion of objects, while Maxwell's theory brilliantly unified electricity and magnetism. However, there was a growing conflict between these two cornerstones of physics. Maxwell's equations predicted a constant speed of light, which contradicted the Galilean transformations of Newtonian mechanics. The Michelson-Morley experiment attempted to detect the luminiferous ether, a medium through which light was thought to propagate. The experiment's failure to detect the ether shook the foundations of physics. In 1905, Albert Einstein proposed a radical solution with his special theory of relativity based on two fundamental postulates. The first postulate, the principle of relativity, states that the laws of physics are the same for all observers in uniform motion. That is, there's no way to determine absolute motion. Only relative motion is meaningful. The second is the constancy of the speed of light. The speed of light in a vacuum, approximately 3.0 times 10 to the 8th meters per second, is the same for all inertial observers, regardless of their relative motion or the motion of the light source. These two postulates combined have some profound implications. So let's now explore this. Special relativity requires us to rethink our notions of space and time. We must combine them into a four-dimensional continuum called space-time. Classical physics uses Galilean transformations to relate coordinates between different inertial frames. But these transformations don't preserve the constancy of the speed of light. Instead, we need the Lorentz transformations. Here are the equations for a frame S' moving with velocity v along the x-axis relative to frame S. T' equals gamma times quantity t minus v times x divided by c squared. X' equals gamma times the quantity x minus v times t. Y and z remain unchanged. Here, gamma is the Lorentz factor, defined as 1 over the square root of 1 minus v squared over c squared. These transformations lead to some surprising effects. First, time dilation. Moving clocks tick slower relative to stationary observers. The time interval between two events becomes smaller and smaller as relative v increases. Second, length contraction. The length of an object moving at high speeds is smaller than it would be if measured at rest. The length in the x direction shrinks, as given by the x' equation. The concepts of momentum and energy also need to be revised in special relativity. Classical momentum, P equals mv, is not conserved at relativistic speeds. The relativistic momentum is given by P equals gamma times m times vector v. Likewise, classical kinetic energy is not accurate. The relativistic total energy is E equals gamma mc caret 2. The famous equation, E equals mc squared, represents the rest energy of an object, the energy it possesses solely due to its mass. The kinetic energy is then the total energy, E, minus the rest energy. A crucial concept in special relativity is the space-time interval. It's a measure of the separation between two events in space-time, and crucially, it's invariant. All inertial observers agree on its value. The space-time interval, denoted as delta s squared, is given by c squared delta t squared, minus delta x squared, minus delta y squared, minus delta z squared. We can categorize intervals into three types. Time-like. Here, delta's s squared is greater than 0. Space-like. Here, delta's s squared is less than 0. And light-like, where delta s squared equals 0. Imagine a flash of light emitted at a point in space-time. This forms a light cone. Events are inside or outside the cone. If it's inside, the event can be caused by another from the point. If not, it cannot. It's important to remember that Maxwell's equations, the foundation of electromagnetism, are already consistent with special relativity. In fact, they are Lorentz invariant. This means that the electric and magnetic fields transform between different inertial frames in a specific way, dictated by the Lorentz transformations. What appears as a purely electric field in one frame might appear as a combination of both electric and magnetic fields in another. The Lorentz force on a charged particle, which describes its motion in electric and magnetic fields, is also fully compatible with relativistic mechanics.